All right, today we begin our unit on that leads us into derivatives, which is one of the most important topics in calculus. There's basically two halves of calculus: differential calculus, and that has to do with the study of derivatives. Okay, and we're talking about basic calculus here. There's very extended things that can be learned about calculus, but if we're talking about a traditional calculus sequence, there's basically two important concepts: differential calculus, differential calc, and integral calc. We will spend the next couple months, probably until shortly before Christmas, working with differential calculus. Hopefully this year, before Christmas, we will get to integral calculus, just in case we have a lot of snow days. We have to start this whole thing by going back to geometry and reviewing what a secant line is. If I talk about a secant line for a certain function, whatever that function may be, let's say that it's something like that. Let's say that's my function, f of x. Well, if you remember, and you may or may not, a secant line is a line drawn through 2 points on a curve. Okay, this is what we call a secant line. Don't confuse that with our trig function, secant. Okay, this is a secant line. All right, drawn through 2 points on a curve. And we're going to use that as we start talking some more. We've already touched on it, this idea of the average rate of change. When I talk about an average rate, and I want you to underline the word average, because most of this semester we're not going to be worried about the average. We're going to be worried about the instantaneous rate of change. But we have to begin by understanding what an average rate is. We've already talked about this a little bit. It is the change in distance divided by the change in time. For example, if I hop in my car and I travel 300 miles in 5 hours, my change in distance was 300 miles. My change in time was 5 hours. My average, again, average speed would be 60 miles per hour. That's an average. Because remember, that doesn't calculate, or it doesn't help us know what happens when, if I do those 300 miles driving to Indiana, I have to go through Chillicothe, and that means I have to go on Route 50, and that means I have to go around Maxwell Curve, which means I usually have to drive about 40 instead of 60. Okay? And there's places where maybe there's a straight stretch on 50 on the way to Chillicothe, and maybe I drive 63 instead of 60. Okay? So this is an average speed, not a speed at an instant. And when we talk about, and this was what we kind of touched on in the last section, we said distance always corresponds to the y-axis. Distance always corresponds to the y-axis, or what we call the function values. Time is always going to correspond to the x-axis. Okay? Very important. So let's jump right to an example with average speed. Very basic example. Find the average rate of change. Find the average rate of change of f of x equals x cubed minus x over the interval 1 to 3. So we're going to look for an average rate of change of that function over the interval 1 to 3. So guess what? All we got to do is follow our rule. Change in distance over change in time. Once again, do you remember the lame song that I taught you? Delta y over delta x. Guess what? I told you it was going to become very important, and you're soon going to find out why in the next week or so. Change in distance means the change in the function values over the interval. Okay? Change in the function values or change in y values, right? So what I'm going to do is I'm going to find f of 3, and I'm going to subtract f of 1 on the top, because I'm trying to find how far I went. And in this case, we're doing that in relation to a function. On the bottom, it's the change in time. So that's just 3 minus 1. Okay? So now I can evaluate those function values. F of 3 would be, what, 3 cubed minus 3, so that's going to be 24, minus f of 1, which would be 1 cubed minus 1, which is just going to be 0, all over 2. So the average rate of change, okay, the average ROC, I guess you could say, is 12. Average rate of change is 12. And, you know, we could, if we wanted to, look at that on the graphing calculator to see what that means. Okay? If I were to look at this graphically, which right now we're mostly concerned with it analytically, I want you to see it graphically though as well. If I were to graph x cubed minus x, I would have this thing that maybe it kind of looks like that, all right? And we could find our zeros, of course. You know, I could set x cubed minus x equal to 0 and take out an x. Looks to me like my zeros are going to be at 0, negative 1, and positive 1, okay? What we did was we took a secant line, basically, from 1 over to 3, okay? Way up here, we said the coordinates of this point were 3, 24, okay? And the coordinates of this point right here were 1, 0. And then essentially what we did, Christmas time is only a couple months away, so I will make this a Christmassy picture. When we found out the average rate of change on that thing was 12, what was it really telling us? What is, very good, the slope. The slope of this thing is 12. That is my average rate of change. Okay, it essentially corresponds to a slope of a secant line. Okay, a slope of a secant line. Okay. Now, I want you to turn in your books, and I'll pause the video to give you a second to go there, to page 87. Example number 2. Okay, if we look at page 87, we have a lot of information. They give us this graph, okay? And we can probably add this into our notes. The graph kind of does one of these numbers, all right? And if we read through, it's talking about the rate at which populations grow in a laboratory, okay? And this particular example talks about how the number of fruit flies grew in a controlled 50-day experiment. The graph was made by counting flies at regular intervals, plotting a point for each count, and drawing a smooth curve through the plotted points. Okay? So that's our graph. Now, they say in example 2, use the points 23, 150, that is point P, and point Q is 45, 340. Okay? Use those 2 points in figure 2.27 to compute the average rate of change and the slope of the secant line, PQ. Now this is one of those problems that has a lot of words, but really a very simple solution. Okay? So we have this point, 23, 150. Okay, just come straight up here. That's got to be a 150. This is the point 23, 150. And then we have the other point, 45, 340. So I come over to 45. And we're told that that point way up here is up at 340. So this is the point 45, 340. All we need to do is find the average rate of change over this interval. So it's basically the slope of the secant line. All right? Very simple process. I'm going to, once again, find change in distance or change in y over change in time, or we could think of change in x. So it's going to be 340 minus 150 all over 45 minus 23. 190 over 22, looks like, which is 8.63. Somebody asked about the units on the last one. Do we have a unit on this one? Yes. Isn't it talking about the growth of flies in a laboratory per day? So this would be an average rate of change or an average increase of 8.63 flies per day. And yes, in AP Calculus, we are often concerned with units. So in this case, we do want to have that right. And we will stop there for today.